Hello, let's take a look at section 1.8 in pre-calculus, and in this particular section we're going to take a look at inverse functions. Inverse functions. The definition of an inverse function is if we let f and g be two functions such that f of g of x is equal to x for every x in the domain of g, and g of f of x is equal to x for every x domain of f. We consider that to be an inverse function. The notation for an inverse function is f to the minus 1, and this is f inverse, f to the minus 1. This is not the same as a negative 1 exponent here. So basically what we say we do here is if we have a set of ordered pairs x, y, and by reversing the components resulting in yx, this may or may not be a function, but the inverse function has a special undoing relationship. And we'll look at that relationship here. And as you see here, that is not the same as f to the negative 1 or 1 over f. Functions are a subset of functions. They're special functions where for every x there's only one y, and for every y there's only one x. That's what defines a function. So the definition of a function is for every x there's only one y value, and we call this the inverse functions are one-to-one functions. So if we take a look at the inverse function and we let f of x equal x minus 300 and g of x equals x plus 300, then f of g of x is going to be x. And so if we look at the table itself and we look at the x and the y values and we swap these values and they're the same values, then this becomes a function. And the inverse function is a function as well. So let's look at this example here. Find f of g of x and then g of f of x. And so what we want to do here is we know how to find the composite f of g of x is equal to 3, and we'll plug in g of x times x minus 2 over 3 plus 2, and our 3's will divide out, our 2's will subtract out, we end up with x. And then we look at g of f of x as a composite function. So we plug in 3x plus 2 minus 2, and then we divide by 3. Our 2's will subtract out, our 3's will divide out, and we're left with x. So this shows that the inverse function is a one-to-one function as well. Find f of g of x and g of f of x to show that they are inverse functions. So f of g of x is equal to 5, and I'll write it in red. We'll plug in g of x minus 3, and we get a value here of x, and then we have g of f of x is equal to, and we'll plug in f of x plus 3 over 5, and we get a value of x there. So they are inverse functions. Now finding the inverse function is our next order of business here. In order to do that, there's a couple of steps that we go by. The first step is we replace f of x with y in the equation. Then we interchange x and y, and we solve this equation for y. If this equation does not define y as a function of x, then the function does not have an inverse function. And if the function has an inverse function, we denote that by f of negative 1, or the inverse function of x. So here's an example. Our first step is to replace f of x with y. Our second step will be to interchange x and y's. And then our third step will be to solve for y in terms of y here. And then our fourth step is to replace that with the notation there. So let's do one together. So we'll actually substitute y in place of f of x is equal to 7x minus 1, and then we'll interchange x and y's. And then we'll solve for y. So if we solve for y, y is going to be equal to x plus 1 divided by 7, and then we write the inverse notation. x plus 1 divided by 7. So that's the inverse function there. Let's look at another example. We substitute y in place of f of x. We interchange x and y. I do apologize for the sound. I have not figured out how to carry that out yet, or how to get rid of it. And then we solve for y, and what we end up with is y is going to be the cube root of x minus 4, and we write our notation is equal to the cube root of x minus 4 there. And here's another one, and I'll just write your answer here, and you can go through the math on this one. The inverse function is equal to 3 over x plus 5. So just remember, let f of x equal to y, interchange x and y, and then solve for y. Now we can also do a horizontal test to determine whether or not it has an inverse function, or a one-to-one test as well. So if we actually do the horizontal test here, what we actually do is we put a horizontal line through the graph of the function, and if it touches the graph more than one point, then it does not have an inverse function here. So it says the function has an inverse function if there is no horizontal line that intersects the graph at more than one point. So in this particular case here, we see that it actually intersects at point 1 and point 2, so it does not have an inverse function here. If we take a look and apply the horizontal test here, we see that part A has an inverse function, part B does not, part C does not, but part D does. B and C does not pass the one-to-one relation. I graph the following function to tell whether or not the function has an inverse function. So if we actually graph this particular function here, we know that this is the radical. We should know how to shift now. If we have a negative 3, that means we're going to shift to the right 3 units, and this is going to be the square root graph, so it'll actually tail off in that direction there. If we apply the horizontal line test, we find that it only touches 1, so it is, or it does have an inverse function there. Let's take a look at the absolute value. We know the graph of the absolute value. We have a negative 1 here, so we know what's going to happen is it's going to go in the opposite direction, so we'll move it in this direction here, and the absolute value is the graph of a V. And if we apply the horizontal line test, which I'll use this shade here to apply the horizontal line test, we see that it touches at more than one point, and because of that, it is not a function. Let's look at the graphs of the function and the inverse function here. If there is a relationship between the graphs, a one-to-one relationship, and this inverse is because the inverse function has ordered pairs, what we do is we actually just alternate the values. A become B, and B become A, or X become Y, and Y becomes X. So we create what we call a reflection, and we've seen the reflection, or a flip, and I'll put here we flip the graph, and we actually create a line through the origin point, and we flip it because it's symmetrical about the origin point. So here we see the graph of f of x, and we see the graph of the inverse function there, and we see the symmetry graph here. If we apply the horizontal line test, we know this is a one-to-one function, so we know that this does have an inverse function. Is this function, if this function has an inverse function, then 1 over, or then the graph of its inverse function is on the same graph. So let's take a look here and look and see. This is kind of tricky, but I do want to go through the math. We'll actually let y, substitute y in place of f of x, and then we interchange x and y according to the steps, and then we solve for y, and as we solve for y, we're going to end up with the same equation. So what we end up with, we do have an inverse function, so the inverse function is the same as the function itself, so the graph is the same graph here. What about this particular graph here? If we look at the inverse of this particular graph here, and we can actually create a line through our axis of symmetry here, And if this starts at 3 and 0, then our inverse is going to start at 0 and 3. So we'll just start at this particular point here, and it actually tails off in that direction there. So that will be the inverse function. So this will be f to the, or the inverse function, and this would actually be the function itself. And let's take a look at this one, the inverse function here. If we look at the inverse function and we substitute the inverse function of x, is going to be the cube root of x. And this one gets kind of tricky, so I'll draw it. It actually creates like a little 8 right in here, and it tails on off, and it tails on off, and then your axis of symmetry is straight down the origin point. Excuse my line there. It's just hard to draw with this particular pad here, but this does have an inverse function, and if we apply the horizontal line test, it applies as a one-to-one function. Applications of inverse functions. We look here and we have Fahrenheit, degrees Fahrenheit, and we see degrees Fahrenheit is f of x is equal to 5/9 x plus 32. It's a one-to-one function because it's linear. And then if we find the inverse, and we actually interpret the inverse to be Celsius, we actually substitute y, we interchange x and y's, and we solve in terms of y, and what we find out is that the inverse function is the Celsius formula. So that's how we derive Celsius, or degrees Celsius versus degrees Fahrenheit. It's a one-to-one function. So let's find the inverse function here. If we substitute y in place of f of x, and then we interchange our x and our y's, and we solve for y, we're going to end up with y is equal to 2x plus 5 over 4, and we write the inverse notation, 2x plus 5 over 4, and we select the correct answer. And here we want to find the inverse function, so we substitute y in place of f of x, then we interchange x and y's, and then we solve for y. So we actually take the